Okay, so this is where we left off with our warm up. And we realized we got to a place where analytically we can't calculate this double integral. But I'd like us to picture what it looks like visually. So if you recall, the double integral of a function of two variables can be interpreted as the signed volume of that function over your region R. This picture is totally not going to do justice to it, so let's go ahead and put up an actual picture. Okay, so this is actually what the region looks like, way better of a picture. This is my function z is e to the negative x squared minus y squared, which is a Gaussian. And then this is the semicircle, which is the region I'm integrating over. And so you can see we can interpret this double integral as this volume of this half of the mountain. And we can interpret when we try to integrate in Cartesian coordinates with respect to dy dx that we are chopping up this region into these rectangular boxes along constant x and constant y values. So we can add, let's do more just so we can see. Let's do maybe 20 in both directions. You can notice as we take the limit and add more and more, we're going to get the actual volume underneath this mountain. But analytically, this is not working too well for us to chop up the mountain this way. And so the question is there a more natural coordinate system we could use to chop up a region that looks like this? And if you were thinking, hey, the bottom of the region looks like part of a circle, I'm thinking I should use polar coordinates instead, you are right. So let's talk about what it would look like instead of chopping up for constant x and constant y, if we chop up for constant r and constant theta. So we can make a little picture here. And notice, let's start with way less so you can see what it's going to look like. Let's do 10. Constant r and constant theta is going to give us, I like to call it this polar graph paper, kind of looks like this little spider web shape. But that's going to lead us to these little, I mean, there's still these three-dimensional objects, but they're no longer rectangular. They're kind of like these little curved curved box segments. And we're going to be adding the volume of those up as we chop up this region into more and more of those. So let's see analytically how we can do this. And it's going to turn out to be a much easier way, and actually the only way that we can calculate this particular double integral that we started with. Okay, so this handout, the blank handout's available on Canvas, and I recommend you print it out and write out the notes as we're going through. We're going to start with a quick review of polar from Calc 2. And one of the first things is we define the pole, which usually we put as the origin. And we define r to be the signed distance from the pole. So in this case, x squared plus y squared is r squared. And theta is going to be the angle from the polar axis, positive angle. In this case, our polar axis is listed as the x-axis. So we have tangent of theta is y over x, assuming x is not 0. And then we can go backwards. Given r and theta, we can figure out what x and y are just by using some trig. So notice that cosine of theta is x over r, if there's x and here's y, which means that x is going to be r cosine theta. And then similarly, we're going to have x is r cosine theta, we have y is r sine theta. And we're going to, and we can visualize this here as I pick any point in the xy plane on the right, and you can find the corresponding point on the r theta plane on the left. And so let's use this to help us come up with a way to map regions in the xy plane to their corresponding region in the r theta plane. Okay, so let's look at both of these examples. Let's start with part A, and we can describe this in polar coordinates by noticing that r in polar
in this region goes just between 1 and 2. And theta in this picture starts at 0, and the biggest it can be is pi over 4. So notice if we were going to go sketch the equivalent region in the r theta plane, so let's let this be r and this is theta, then it would be, this goes out to 2, this goes up to pi over 4. And so this is going to give us this rectangular region. Oh, sorry, starting at 1 to 2. So it's going to give us this rectangular region in polar. And then similarly, part B, which is the region we're integrating over in our warm-up, we can rewrite this in polar by noticing that r goes from 0 to 2, and theta in this case goes from negative pi over 2 to pi over 2. So this gives us another rectangular region in the r theta plane. So both of these types of regions in the xy plane are what we call polar rectangles. Let me sketch this here, 0 to 2, and then let's say this is pi over 2, negative pi over 2, so it's this whole region. Okay, and this is important because it's much easier to integrate over a rectangular region than it is to integrate over a non-rectangular region. And so this type of region is called a polar rectangle. And polar rectangles are going to be great candidates for, and that's what I'm meaning by this type of region, because when you translate it to polar, you get rectangles. And so any regions like this are going to be great candidates for switching to polar coordinates, because then in polar, we're going to have nice, easy bounds. So let's actually go back to the warm-up and think about that a little bit, about how we could potentially set this up. Notice in the warm-up, we were trying to integrate, I'm just going to write it in general here. We were trying to integrate e to the negative x squared minus y squared over this region, where this was my region R. And now the idea is, how could we switch this to my new polar region? So I'm just going to call that G, that polar rectangle. How could we switch the integrand into polar? And then how could we switch the dA to be equivalent? So what is dA going to be in terms of r theta delta r delta theta? The integrand here you can see is going to be pretty easy to translate to polar, because negative x squared minus y squared, notice x squared plus y squared was just r squared. So this is just going to be negative r squared. But then the question is, what is this dA in polar? Because our bounds, we know how to do. This is going to be that rectangular, the G that we wrote is going to become the rectangular region here that goes from negative pi over 2 to pi over 2, 0 to 2. This is r, this is theta. So we know that. But how can we make sure that we end up with an equivalent volume for that half of the mountain, then we don't actually change things up by changing the region? All right, so I want to end up with the same volume for both of these, even though I'm now changing the region to a nice rectangle instead of a semicircle. So let's do one more visual before we go to the algebra. Okay, we're gonna do a quick visual before we analytically calculate dA. So what we're looking for is, or we're asking is, when we switch to polar coordinates and when we take a region like this in the XY plane and switch it to a nice polar rectangle, what does my dA become? And visually, dA is the area of this little blue polar rectangle. Because when we go chop up our region, our mountain, we're going to take the area of the base times the height. So back in the picture, in order to find the volume of one of these little curved polar boxes, I need to know what's the area of the base, which is one of these little curved polar rectangles, times the height. So my goal is to figure out what is the area of one of these blue polar rectangles in terms of r, theta, dr, and d theta. And we can see just visually that it shouldn't be that the area of one of these blue rectangles is just dr d theta. Because if you look over here on the left, this represents dr, change in r. So my change in this r-axis, and the height represents d theta. And so as I move around blue, I can realize that my blue rectangular areas are getting bigger, right? But those red ones over there are the same everywhere, no matter what my r and my theta is. So dr d theta on the left can't actually equal dA on the right. As you can see on the right, these areas are growing. And in particular, they grow. Notice what happens here. If I move in theta, these blue areas are not actually changing, which is going to be insightful. So for a given theta, my dA should stay fixed. But if I move in r, my dA is definitely changing. And so we're going to now go calculate how we can actually find the area of one of these little polar subrectangles in terms of r, theta, dr, and d theta. And that's what will go into our integrand when we're replacing dA in polar coordinates.